We're going to start our investigation of chemistry from the very early days, and we're starting the late 1600s here, and there was an element that was proposed called phlogiston. And chemists looked for phlogiston for about the next 120 years after its proposal in 1680. We're going to go through the processes of them looking for it and the experiments that led to them coming to a better understanding of chemistry. Fire has long fascinated people, and by the time that the late 1600s, early 1700s came along, there was this idea of trying to figure out why things burn. So people were looking at this proposed element phlogiston, and the idea was that materials that burn contain phlogiston, and things that can't burn don't have phlogiston. So one thing that metals can do oftentimes is if you heat them up, they can react and sometimes burn. So they must contain phlogiston. And then animals, like we release phlogiston into the air. And if we can't release that phlogiston into the air, we'll die. And it turns out this is also the idea of why animals aren't very good at burning. On the other hand, plants are really good at absorbing phlogiston. They absorb it from the air, and that reason that they absorb it from the air, when they absorb it from the air, that makes them flammable. So we can burn wood very easily. And when there is too much phlogiston in the air and around something, burning will stop. So what we're going to do now is we're going to look at what happens to a candle that's burning. We're going to take it and put a cover over top of it. So let's just observe and see what happens. So there's the candle, it's burning. We put a glass container over top of it. Now, back in the 1700s, we would think that the candle is burning and releasing phlogiston, and now that container, the glass jar over top of it, is absorbing and absorbing and absorbing phlogiston. So as it absorbs phlogiston, the air is filling up with phlogiston, and now the candle is gone out. So this candle stopped burning because the air around it absorbed as much phlogiston as it possibly could. No more could fit into it, so no more phlogiston can be released by the candle, and burning stops. The problem was that people couldn't find the phlogiston, though. People were looking for this mysterious substance, and they couldn't find it, so they kept on looking for it. They would take that container, for example, the one that we had just seen, and they would open it up, and they would try to collect it, and they could find all the other gases that they were sort of looking for, but they couldn't find the phlogiston. So where was it? Now, there were other observations that were being made at the time that were somewhat interesting. So, for example, here we have in the jar, instead of just regular air, I have collected what at the time was known as brewery gas or fixed gas. This is the gas that was first collected actually when beer was being made and brewed in England in the 1600s. People were fascinated by this gas that was given off when they collected it, and one thing they noticed is that when it was put over top of candles, that instead of burning for a little while, the candle goes out immediately. So it must be that that gas was filled with phlogiston. Again, really hard time finding it, but this gave credence to the idea that we release phlogiston, maybe yeast releases phlogiston as well. Okay, so by the 1700s, late 1700s, there were some interesting observations that were being made. And one of these was by a British person named Joseph Priestley. He was heating up what we call the calx of mercury, sort of reacted mercury. And he noticed a gas was being released, and he captured the gas. Over here on the right side, you can see an image of experimental setup. And one of the nice things about the calx of mercury is that he was able to sort of put mercury in the bottom of his tube with a little bit of that calx of mercury on it. So this, what we now know as mercury oxide on top of it. And he was able to heat that calx of mercury by using sunlight. Actually, he just used a big magnifying glass and heated it very strongly. And he collected the gas that was given off by this calx of mercury. And he figured out that it made candles burn brighter. And when he would put a mouse inside of a container that contained this gas that he had just given off, that they would live a lot longer than if you put them in a container that just had regular air. And he thought it was agreeable to breathe. So he thought, well, okay, what I've just created is an air that doesn't have any phlogiston in it. So if the mouse can live longer and the candles burn brighter and longer, then this air doesn't have any phlogiston at all. So I'm going to show you a video of that next. So what we have here is, in my hand, I have a container that's filled up with that dephlogisticated air, and there's a candle on the table there, and we're going to put the dephlogisticated air over top of it. Now, and you see initially the candle burns a little bit brighter, and it's burning for a longer time. Okay, it's still burning quite brightly, still burning brightly, still burning brightly. So, and the container itself has water vapor on the inside. That's because I had to collect this dephlogisticated air over top of water. I didn't have a mercury bath to collect it over. And it's still burning, still burning, still burning. And now the air must be filling up with phlogiston. And finally filling up with phlogiston, and the candle goes out. So the candle burned much longer this time with this dephlogisticated air. Another observation about the dephlogisticated air is even if you put an ember inside of it, it starts things that will start to combust easily. So the phlogiston will jump out of the material and go into the environment because there's so little air in so little phlogiston in the environment that phlogiston, if it has the ability to go into the air, will go into the air. So these are all observations that Priestley made back in the late 1700s. So Priestley had this dephlogisticated air that he was able to produce and didn't really know what to do with it. So he showed this gas to Lavoisier, who was the top chemist of his day. Lavoisier was French, lived in Paris, and there's a picture of him there on the right with Lavoisier and his wife Marie Pauls. The two of them were really quite a dynamic team, and they were unbelievably productive chemists. So, unsurprisingly for the time, Lavoisier got all of the credit, but they both worked together. Lavoisier was one of the wealthiest men in France at the time, and so he could outfit his own home laboratory, essentially, and as he was outfitting it, he was able to bring in all sorts of devices that would allow him to collect things and to measure things. So he did experiments with this gas. One thing that Lavoisier already knew was that some things, especially metals, become heavier when they burned or rusted, and that didn't agree with phlogiston theory. Phlogiston, if it's a material that's given off, should make things lighter when they burn. But in fact, when iron forms rust or when iron burns, it becomes heavier. Same thing with the zinc. So this gas that was collected by Priestley seemed to react with metals in the exact same way that metals react when they're burned, just faster. So, and what Lavoisier noticed is that dephlogisticated air, the mass of the air or the gas in that sample decreased, and the mass of the metal increased by exactly the same amount. So he realized that there was something going from the air into the metal when it reacts. So, according to Lavoisier, it seemed that the gas that Priestley isolated was a gas that is required for combustion. And so he knows that this phlogiston thing isn't real. Phlogiston isn't given off. And so he actually identifies it as a new element. And that element we now know is oxygen. It reacts with nonmetals to produce acids. And in fact, that's what oxygen means in Greek. It's something that generates acids or generates sharp things. So by the way of this reaction and all the other reactions studied by Lavoisier in closed systems, he actually figured out something else, and that's really important. That's the mass of the reactants in a reaction, the things that are reacting, is always equal to the mass of the products of a reaction. Matter is never created or destroyed in a chemical reaction. So this is known as the law of conservation of mass. These were Lavoisier's two big contributions to chemistry. Actually, he had several others, His life was cut short. In fact, it was cut short not long after writing about the discovery of oxygen in a textbook that he wrote. It was during the time of the French Revolution. Lavoisier actually met the guillotine because of the fact that he was a tax collector for France, and was able to maintain a portion of those taxes as his own income. So his life was cut short, but as it was cut short, two huge contributions to chemistry, and really probably Lavoisier was the first real chemist, like we think of as chemists, people who are collecting data and working with data to make observations about how chemical reactions actually happen. So what we're going to do now is we're back to our original candle. And what I want you to do is write to me three things. You saw three candles burning. In this case, we're putting the cover over top of it and the candle is extinguished. I want you to propose a reason why it's extinguishing, both from the phlogiston point of view and from Lavoisier's point of view. Then we saw the fixed gas, or the brewery gas, which is now known as carbon dioxide. Why did the glass container full of carbon dioxide cause the candle to go out immediately? And then why did the container that was filled with the dephlogisticated air, which we now know as oxygen, why did the container that was filled with oxygen make the candle burn longer and more brightly? So those are sort of our three check-in points right now. And from there, we'll go on next and take a look at Dalton. Dalton was the first person who proposed the existence of atoms in a real and concrete way.